I saw you.
Hello, everyone.
I saw you.
Thank you for coming today. Today is our final speaker for the seminar series. We will in 2 weeks have a poster session that many of the students in this room are presenting at, but I hope the rest of you will come and join and look at their research and work that they've been doing. I will let Jeff introduce our final speaker. Sorry.
All right, good morning. So our final speaker for the series is Dr. Ashley Schulz. She's an assistant professor at Mississippi State. She did her undergrad at Mizzou, Missouri, master's at UGA, right, and then PhD at Arkansas State. So she works a lot with forest health, invasive species, and she's going to talk to you about forecasting some of those invasive species today.
Yeah.
So this is Ashley.
So yeah, like I said, I'm Ashley Schulz. Y'all can just call me Ashley. I was telling Jess earlier that back in the day when I was fresh out of like grad school and stuff, I rehearsed how to do my presentations, but now I just kind of like mosey around and like kind of like I do when I'm teaching. So if you have questions along the way, you're also welcome to ask, but we can also save them for the end, whatever y'all would like to do. I'm going to talk to you today about some research that I've been working on for 9 years now. So I started it whenever I was a PhD student and kind of transitioned into postdoc, and I'm still working on it now because it's a continuation. We have several papers out. We have more work to do still. So it's a big story and a lot of fun. And I think it's something that goes really well for like a 45-minute presentation, as opposed to sort of putting together all of my different students' projects and talking to you about cobalt grass and southern pine beetle and urban forestry and like all the different projects that I work on. So without further ado, start with the beginning. So in the beginning, our working group was sort of comprised of a few individuals and it has since kind of grown. So I'm not the only person who has worked on this project that I'm going to talk to you about today. There are many, many people that have kind of come into play here and have contributed knowledge and I don't know, background information and data wrangling and a lot of PI. So I was one of the postdoctoral fellows. I started on the project as a PhD student, but then kind of took over as a postdoc, and then now I am an assistant professor and working with Catherine Thomas and Angela Meck to continue this for writing grants, writing papers, continuing this work that I'm going to talk to you about today. So I wanted to kind of start up front and give thanks to all of these people because it was not just I who did all of the work that you're going to hear about today. Collectively, we are the High Impact Insect Invasions Working Group. So whenever we started out around like 2016 or so, our sort of main overarching question was, how do we sort of predict the next high impact insect invader? And so we have these mega invaders that have catastrophic impacts to our North American forest ecosystems. How do we differentiate those catastrophic insects from those that are more benign, that maybe come in, non-native insects that don't really have much of an impact at all? How do we predict those ones? And so that was kind of the overarching question for our entire project, and still kind of is to this day. And I'll tell you about a little bit later towards the end of this presentation. So how do we predict the next high impact insect invaders? We kind of went back to the literature, talked about it a lot, debated a lot. We locked ourselves in a room together for a week at a time for over 2 summers and hashed out everything. And initially we kind of focused on the insect trait stuff because that's typically what people focus on and have focused on in the past. But we're like, well, what if there are other factors that come into play here that may be driving insect impact? So our hypothesis, which was originally documented in Angela's paper published in 2019, kind of just said that non-native insect impact is influenced by, yes, insect traits, then also what about the traits of the host? Think about how host naivety in terms of defense mechanisms could be driving insect success? What about the relationship between the host in the native range and the host in the introduced range in North America? And then also, are there any other insects here that are related to the insect that's invading that could be buffering that effect? So the tree may already have evolved defenses against insects in that genus, for example, or maybe there are natural enemies that can feed on or predate those insects, thus sort of limiting their success. So our initial hypothesis considered these sort of 4 traits as things that could potentially be driving non-native insect impact. So the next step was to do a ton of data synthesis. We called this data synthesis time in the overall database that we developed, the traits and factors catalog. So collectively, that's just anytime you see the traffic down there, that's what that refers to, traits and factors. So this is sort of how we developed that process, that database. So whenever we started out, we took a list, we compiled a list of all of the non-native insects in North America from Acama's list and Yamanaka's list, and then some others that kind of came about after those lists were published. And we kind of broke them down. So there were like over 500 insects on that list. And we broke it down into sort of different categories. So we had our conifer specialists, so they fed on only, fed on at least 1 of 3 at the time, conifer families. Now it's just down to 2. We don't have Taxodiaceae anymore in North America. Second part, hardwood specialists, and then part 3 will be non-native forest insects, where we added in the generalists. So this first part, when I talk about traffic and the models, I'm gonna talk mostly about the conifer specialists and hardwood specialists, but then I'll work in the generalist too towards the end. So as we were going through and looking at our insects and synthesizing data, we wanted to kind of figure out how to, in an unbiased way, assess their impact, which is really hard to do sometimes. So we came up with, and this alone was 3 days of debating within our group. We came up with this 9-point scale of impact ranging from 1, which was no damage. Doesn't mean that there necessarily was no damage, it just mostly means no documented damage. Some insects have a very long life phase. They're not noticed in the environment. Nobody sees them, nobody documents them. So if there was nothing there, we just kind of gave them a 1 and said, nothing there. And then it ranged all the way up to 9, where the insect caused functional extinction of the host. So think of like emerald ash borer level insects. So for analysis, we kind of, especially the conifer specialists, we reduced it down to 2 levels, so not high impact and high impact. And then we did some further analysis. So I had a paper where we kind of assessed how everybody assessed, all of the researchers within our group assessed each insect and decided whether or not this scale was actually good, or if there was still a lot of like confusion in how people would rank things. And we actually had quite a bit of overlap in how we assessed insects. So we kind of ran with the scale as we had created, but I mean, like all good research should do, we come back to the question and say, why did we do that again? Why don't we do it this way? So, but time and time again, we revisit the same conversations and say, this is why we did it. And we still stand by that this was the best way to do it overall. So yeah, impact was really important for deciding how we were going to rank insects as we were synthesizing their data. So overall, we had 58 conifer specialists, again, that only fed on Cupressaceae, Pinaceae, or Taxodiaceae, 100 hardwood specialists, and then overall we merged those 2 and then added another 90 generalist insects. And these were our distributions of families. Most of the insects were hemipterans on the Acama and Yamanaka lists. So we tried to reflect the same sort of percentages as what were on those lists in terms of our breakdown. All of the high impact insects were included in the analyses because we wanted, there aren't that many. I mean, it's a good problem to have. We don't want more high impact insects. But overall, some people say, well, what if you excluded this one? No, we went through all the lists and we found all of the high impact insects and included them. Short of some like, we didn't include Asian longhorn beetle because it's still fairly new. Y'all have that here now. Dr. Coyle works on that a lot, and maybe even just.
I don't touch
You
it.
know, Dr. Coyle works on that. So things like that are just too new. They haven't established or had a chance to establish, so we didn't include those types of insects. But if they had been around for a while and had an active chance to be able to establish and have a high impact, we included them in there. So these are our distributions. And then for each insect, so we ranked impact on the host in North America that they fed on. We synthesized insect traits from the literature. So feeding yield, what was the most impactful feeding yield? Were they root feeders, wood borers, defoliators, gall makers, that sort of thing. Everything about the insect that we could find through the literature. And then we synthesized the North American host traits data, and these aren't all of the variables that we included. These are just a select few. I couldn't include everything on these slides, but big ones included like shade tolerance, drought tolerance, fire tolerance, leaf texture, wood density, that sort of thing. So all of that was from USDA plants. We used that database with all of those variables for consistency. And then for the native and novel host evolutionary history, my collaborator Nathan Havel did a lot of this work. He was able to run the phylogenetic models to get those divergence times using we used a couple different phylogenetic trees in our time over this whole project, because when we first started, there was only one that was out. And then by the time we got around to our second paper, a second one had come out. And so we've been evolving that over time. And then for the native and novel insect evolutionary history, we looked at books and papers and just tried to figure out where there were native insects in North America that may be related to the non-native insects that were coming in. So we synthesized all of those data too. So it was a big endeavor. It took several years. So we started this process in 2016, and I finished synthesizing like the generalist data in 2020-ish. Okay, so the next step, so we built our database, synthesized our data, and now at this point we are building our models. So, we compiled all of our data for all of our different factors. We analyzed the contributions of the different factors for each sort of tree insect pair, and then did some information theoretic approach. I'm not going to go into all of like the significant stats here today, but basically model selection. So if it was less than 2 difference with delta AIC, then we put them together, put the models together. But in our case, none of the models, most of the time, all the time, it came out where there was a top model. And then for each of the different submodels, we call them, so host traits, insect traits, host evolutionary history, insect evolutionary history, those 4, we ran them, or whichever ones were significant, we ran them in a rock plot, receiver operating characteristic plot, and used area under the curve to assess the models to determine if they were better than random, and most of the time, all the time, they were better than random chance. Sometimes just a hair over, but still better. So evaluated the predictive power of our models. So again, I'm going to start out with the conifer specialist and hardwood specialists. All of this stuff that you see here today is published. So the conifer specialist work is in Angela Meck's paper from 2019. The hardwood specialist stuff I published in 2021. I want to refer back to any of that, but I'll just kind of summarize it for you here and now. So with the conifer specialist, whenever we ran insect traits, we found that there weren't any significant traits, which was really surprising to us because we assumed that insect traits would be really, really important for identifying whether an insect was high impact or not. But in this case, it wasn't. None of the traits were significant. None of the models were significant whenever we ran them. So conifer specialist, that insect traits submodel was tossed out. It was different for the hardwood specialist though. But the hardwood specialists, insect traits were significant. And we had a variable called whether the insect was a scolatine or not. So scolatine meaning like a bark or ambrosia beetle. So we found that in our case, scolatine hardwood specialists were more likely to be high impact than any other like feeding yield or any other taxonomic group of insect. And we think that that might be because there are a lot of co-evolved or new associations of these beetles with pathogenic fungi, for example. So that's a whole nother, I've been asked before about whether we would consider creating predictive models for pathogens. That's really complicated, and even this, we tried to dissect it, and it's very, very difficult to predict whether a new association is going to occur or not. So future work, maybe not for me in my career, but I mean, I'd like to tap into it at some point, and I think it is important. We would have to develop a whole new working group with people who may have that specialization. So insect traits overall, not significant for conifer specialists, significant for hardwood specialists. Next up, host traits. So we looked at the traits of the host, things like shade tolerance, drought tolerance, fire tolerance, that sort of thing. And for the conifer specialists, we found that shade and drought tolerance were super impactful. So in particular, shade intolerant and moderate drought tolerance meant less likely to be impacted, and then shade tolerant and drought intolerant meant that the species were more likely to be highly impacted. So, and this is a trend that we'll see kind of more as we go into future slides about shade tolerance and drought tolerance, but there's some thought that there's trade-offs with like growth and defense and stuff. So shade tolerant species may allocate less to growth. But I don't know, but at the same time, they may not be getting enough nutrition or I don't know, something to produce enough defense mechanisms. They may not be able to grow fast enough to offset the impacts of insect damage. So I don't know, there's a lot of uncertainties and hypotheticals about why we're finding the things that we are. But all of those are explained more in the papers that we wrote as far as what we could gather. But if we were to bring a tree physiologist onto the case, onto the project, then I'm sure they could dig into it more perhaps. With the hardwoods, just kind of moving along to them, we found that not shade or drought tolerance, those weren't significant, but with hardwood specialists, wood density was really impactful, where sort of the moderate to high wood density was most impacted. And so we think that may be something along the lines of the trees not, so this again, wood borers being important for hardwood specialists. Trees may not be able to compartmentalize quick enough if they don't grow fast enough. So they have like a softer, I don't know, or more wood density. And then if they grow too quick, then I don't know, it may make them more susceptible. They may, I don't know. So there's a lot of different physiological things here too, but all of it comes down to, at least the way that we related it back, it came down to like the defenses of the plants and how they may respond to insect damage as a result of the physiological differences. One of the big things that we found through this study, so a lot of studies before, like I said, focused on insect traits and host traits, but one of the big things that we kind of started was looking at host evolutionary history. No other study until Angela's paper had looked at that empirically. And so we were able to demonstrate that host evolutionary history is super impactful for predicting insect impact. And what we found with the conifer specialists was that there is sort of this quadratic relationship with the relationship between insects and their hosts, where there's a peak, so an ideal sort of time where the host had perfectly diverged. So if they're too closely diverged, then the hosts may have retained defenses they had evolved evolutionarily with the host from the native range. They're not that diverged, but then if they're super diverged, they're not really recognized by the insect, but somewhere in the middle is sort of the Goldilocks effect, so to speak. I'll talk about that here more in a minute. I'll have a simpler summary, but with the conifers, we used Leslie et al. That was the only phylogeny available at the time for conifers that was published. So we used that paper and we found that folivores sort of fell in this 2 to 3 million year range so if the host had diverged in that time frame, that's where the most impact was. And then around 16 million years ago for sap feeders. So that was sort of the peak time where if the host native range and North American hosts had diverged, that's where they would be most impacted. For hardwood specialists, we actually started that work in 2017. Yeah, 2017. And so by the time we got around to doing our analysis, the Smith and Brown paper from 2018 had just come out, which was ideal because this one was just conifers. The Leslie paper was just conifers. So Smith and Brown included conifers and hardwoods. And so we've been working from that paper and subsequent papers from them for some time now. But that phylogeny, we worked the conifer specialist stuff with the Smith and Brown stuff just to compare. So for hardwood specialists, we found that insects in any gill, we didn't split it out by folivores and sap eaters. There weren't any significant differences, but we found a peak around 9.5 million years. So there's around 18% chance of causing high impact around that 9.5 million years ago mark, or when hosts had diverged around that time. And then for conifer specialists, it was around 3.8 million years, and that's a 20.5% chance of causing high impact. So again, in more simplistic terms, host evolutionary history is sort of something that we've been leaning into more, hence the name of my presentation, like rooted in time, because time really is a big component of this. And as I'll show in the future, evolutionary history is a really big component of our models. So in a sort of simplistic way, the Goldilocks effect is where it's just right, if you remember the old story. So hosts that are less diverged, so you have your North American host that is still very closely related, less diverged to the native range host. The insect recognizes the host, but the host might still retain some defenses that can prevent it from establishing or having significant impacts on the host. More diverged, so on the tail end, so you're talking like oaks and pines or something, like big differences. The hosts are not suitable. The insect may not recognize the plant as a host in the first place. It also doesn't have defenses because it doesn't really need them. But somewhere in the middle is where the insect may recognize the host, but the host may not have the exact defenses necessary to fend off against the insect. So it's just right for the insect, but not a good situation for the host plant in general. We also went back and forth between calling it the Goldilocks effect, and then also like the sweet and sour spot. So sweet for the insect, sour for the host, because it's just not a good situation for the plant to be in. Okay, and then the last one was insect evolutionary history. So whether there's a native congener of the insect in North America. And so with conifer specialists, we found that having a congener did impact the insect's ability to be considered high impact. So whenever there was a congener, that decreased the probability of high impact, likely because there are the plant had co-evolved defenses, or maybe there's some competition between the insect species, or there's natural enemies, for example. Whenever we did the same analysis with hardwood specialists, we did not find any sort of significant trends. So this model was just significant for the conifers, whereas insect traits was just significant for the hardwood specialists, not for the conifers. So whenever we wrapped it all up and kind of looked at both sets of models that were significant for conifer specialists, both and for hardwood specialists, host traits and host evolutionary history were significant for both. We included that in both of them because host traits had for shade and drought tolerance for conifers, and then wood density for hardwood specialists. And then the big difference between them was conifer specialists had insect evolutionary history as significant. Hardwood specialists only had insect traits, not the insect evolutionary history. So we put these kind of together, ran them individually, and then put them together into composite models. So ran the models together into one composite model and tested it out. So you can see the different colored lines here. Host traits is in kind of gold here. We did split out for the conifers. Host evolutionary history was broken out by sap feeders and folivores, so the blue and the green there. And then insect history is in red for this one. So all of them are kind of lower than this black line, which is the composite model. The composite model performed the best. So overall, for this one, it just kind of shows that a combination of factors is really important. Same thing for hardwood specialists. All of the models kind of performed less than the composite model. So overall, the composite model kind of suggests that multiple factors are having an influence on impact. It's not just insect traits, it's not just host traits, it's the combination of them that helps best predict impact. Okay, so whenever we were going through this process, we kind of looked at the different phylogenetic trees that were coming out. We were wondering if there was any sort of difference in them or significant difference that would impact our ability to predict impact. So we ran a sort of separate model that was led by Dan Uden, who's one of our collaborators, and he's at University of Nebraska. And so we took these 4 different phylogenetic data sets, Leslie et al., Kumar et al., Leslie et al. 2018, and then Smith and Brown 2018, and looked at whether the source of the phylogenetic tree had a significant impact on our ability to predict impact. So we found that overall plant phylogeny does not substantially impact risk predictions. There's a lot of similarity in them. There's a lot of correlations among the different phylogenetic trees, which is a good thing. There's not enough variation to warrant saying we need to use one over the other. So if anybody else wanted to do the similar work, they could use any of these phylogenetic trees that they wanted, but keeping in mind that Leslie et al., for example, only does conifers. They don't do hardwoods. So if you're only looking at conifers, you can use Leslie, you can use Smith, you can use whichever one. But if you're using both, then you kind of got to use like Smith and Brown. So, and I think there are more coming out here soon too, at least in my understanding. Another cool application that we kind of tried to demonstrate was testing making predictions. So the composite model that we created for the conifer specialist paper, the Angela's paper, we used the Smith and Brown phylogeny and ran a bunch of insects from Europe just to kind of see the impacts that they would have on North American conifers. So this figure here, I'm not gonna, you all don't have to like look at every little one. This is just a demonstration of what it could look like. So impacts of the non-native insects on the hosts here. So predicted probability of high impact. So on this end, it means that there's likely no predicted probability of impact on this particular species of conifer. And then up further, that has a greater probability of high impact. So around 19% for Picea rubens. And we did the same thing for the insects just to see the the probability of high impact for each individual insect. And then we made that kind of funky looking phylogenetic grid just to see if there were any trends overall, but again, it's very, very fine text, so I'm not gonna reach out to y'all, but this is just this just show how we can apply the situation to make it more useful. And that sort of springboarded us into what I call the iTree pest predictor era. So this is where I kind of came in as a postdoc and started taking over on the work. I did the hardwood specialist work too, or as it kind of transitioned from Angela to me. But for this, I took it over and took what Angela had done with the conifer specialist and hardwood specialists. And then I added generalists and created this sort of non-native forest insects in North America database. So whenever I initially ran the model, I tried it out with all insects. I added the specialist, the generalist, put it all together and ran just one model just to see what would happen. And nothing came out as significant because likely there's conflicting things there. Generalists are going to feed on a broader range of hosts, thus host traits may not be important. They're going to have differences in a lot of their traits themselves and differences in evolutionary history between hosts, because generalists can feed on a broader range and things like that. So it's I don't know, it made sense to me at the time and still does that nothing was significant. So we decided to dig into it a little bit more. And we kind of revisited our idea that we should break out insects based on how many families they feed on. So like the traditional definitions of like monophagy, oligophagy, polyphagy, that sort of thing, and talked about how we could potentially define host breadth in a different way. So we went back to the drawing board. Nathan, I include his picture here, he hates it. Don't tell him I did that. But we created, it's not necessarily a new method. There was a person named Faith back in the 90s who did this work, I think. But he kind of took that and put a spin on it and created this phylogenetic diversity calculation for us, where we can measure host breadth, native host breadth, using the sum of branch lengths. So if we know that the insect feeds on like these species, he adds up all of these branch lengths to determine the phylogenetic diversity calculation. So whenever we did this for our insects, we found that insects range from a PD of 0. So you only have one documented host. Of course, you're not going to have branch lengths to some there. All the way up to 7,723, which was a really, really diverse range of hosts. So whenever we were kind of assessing phylogenetic diversity, we wanted to kind of figure out where the cutoff would be. Like, how do we define a specialist versus a generalist quantitatively? And so again, with our insects, this is the one, Xylosandrus germanus had the highest, 152 tree species and 48 families is what it can potentially feed on. But we wanted to kind of identify where that break was in phylogenetic diversity. So we took all of the evolutionary history models and kind of did sequential like chunking of the data. So in blocks of 250, just to kind of work up and see where there was a difference in area under the curve for predictive ability for those models. And we found a drop around 2,250. And so we were kind of thinking about it. We're like, well, okay, well, could that be a real drop? Is there enough sample size on the north end of it as on the south end? And how would this all, we discussed this for a long time just to figure out if this was legit or not. And we found that it does make biological sense where the cutoff occurs. And so we kind of said, now phylogenetic diversity, our specialists, those with a narrow host breadth, are those that calculate out to have a phylogenetic diversity of less than 2,250, and those that are more generalist, broader host breadth. have a phylogenetic diversity calculation of greater than 2,250. So that analysis kind of helped us quantify what is a specialist versus what is a generalist. And then we also looked at the native host phylogenetic diversity and then native host species to see if there was a curve there, relationship there. So the native host phylogenetic diversity highly corresponded with the number of tree species that the insect used in its native range. So there was a nice relationship there. We dug into it a little bit more. We wanted to look at how insects changed host phylogenetic diversity, host breadth between the native range and North American range. And we found that overall, a lot of insects did sort of remain the same. So about 70% remained the same or even reduced their host breadth, which kind of makes sense. When we looked at it a little bit deeper, we looked at the different biogeographic realms, and we found that Asia overall had the most significant decrease because Asia has a lot of species. So they're going to have some sort of usually decrease whenever they come to North America. Europe also had a small little dip, and then we ran the Palearctic in general overall. The other included like the neotropics, like South America, Africa, Australia, Indo-Malaya, that sort of area. And there wasn't a significant difference between those, though it did drop a bit. And then we found some differences between the different feeding guilds. So gall makers, sap feeders, and wood borers had a narrower host breadth in North America compared to the native range. And that's because they're so highly specialized. I mean, you imagine a wood borer or gall feeder, they're getting into the plant. They're not just like a leaf feeder where they can hop off the plant if something bad happens, like if the plant produces a compound that just doesn't agree with the insect. So they're a little bit more picky in North America. Okay, so moving forward, we wanted to build the same sort of models that we had before, but put it in the context of like all of the insects, not just the specialists. So we reran everything again. Like I said, I put everything into one big model and nothing came out significant. So we ran so many different models, y'all, just to try to figure out what best predicted impact. And what we ended up with are 5 models now. So we have them broken down by conifer hosts, hardwood hosts. For the conifers, we had sap feeder and non-sap feeder categories within the models. And for both of them, we found that shade tolerance and drought intolerance was a significant predictor. And then post-evolutionary history, again, was important. That was that quadratic Goldilocks form of model, the same as before. For the hardwoods, we had 3 models of specialists, spolotines, specialist non-spolotines, and then our more generalist insects. For the non-spolotines, wood borers were still important. Again, think of like emerald ash borer type insects. And then feeding guild for the generalist was also important, but 3 of the 4 high impact insects for the generalist were borers. Think of like spongy moth, for example, winter moth, brown-tailed moth. And then North American host traits, we had not significant for the specialist spolotine or specialist non-spolotine, but it was important. So intermediate shade tolerance was most important for the generalists, and then all of them except for the spolotines were quadratic for the host evolutionary history. I think this one was linear because we didn't have a huge sample size of spolotines, but again, it's one of those things like, yes, you wish for a bigger sample size, but you also don't wish for a bigger sample size. Like, I don't want to pray more high impact insects into existence. So I think if we had more insects in that category though, it would be also, it was verging on quadratic, but it wasn't quite there yet. So it was deemed linear, but yeah, so these were our models, and then we ran Okay, so, and I just emphasized, host evolutionary history was the only factor that was significant for all of the 5 models. So then we ran the composite models just to kind of see how they played out. And in every single case, again, they perform better than the individual submodels, with the exception of the specialist goal time, because the only one was the host evolutionary history model for that one. But yeah, so again, further demonstrating that multiple factors are influencing impact. It's not just insect traits, it's not just host traits, which is what people have historically looked at. Host evolutionary history is important as well. So what do we do with this? Models are cool, but how can we apply this? Well, the latter end of my postdoc and beginning of my assistant professorship, we started incorporating these models into a tool called iTree Pest Predictor that is now available online. And so how the tool works is a user goes in and puts in information about the insects. The most important thing out of this is the host list of native host range hosts, native range hosts. So, but you can also include insect taxonomy, feeding guild, the native range in general, so like Palearctic is the biogeographic realm of the insect. And all that information is going to trickle down into the different types of host trees. So that hardwood versus conifer. If conifer is it a sap feeder, yes. It'll go to this set of composite models. If it's not, it'll go to this set of models. Hardwoods, what is the host breadth? So it will automatically, the tool will calculate that based on the host that you put in. And so narrow range is a skull time, yes, no, decide. Wide range, so greater than 2250, pick that, it'll choose that one. And then with each model that it chooses, it'll put out a tree suitability and predicted insect impact probability table. So you'll get your tree species, North American tree species. We have over 400 North American species in this list. It's going to give you host suitability, so high, medium, low. And then it's going to give you a probability of high impact. We included a color scale for emphasis, but we didn't feel like it was in our best interest or that something we should do to say, oh, this insect is high impact, because it's kind of subjective. It really depends on you and your management. Like an urban forester is going to have a lower risk threshold than somebody who's in like a natural forest. And there's many different things that go into determining whether something is high impact or not. So we wanted to kind of keep it just, here's the data, here are the data, you kind of make the decisions based off of what you think. But so that's generally how the tool works. Again, if you want to visit the tool and kind of explore it yourself, we've got the tool online. There's a little scan if you don't want to scan it later. You can also just Google iTree Pest Predictor if you want. We have information about the project and the information that needs to be included, entered into the tool to use it. And we kind of just emphasize that the tool, the outputs are only as good as the data you put in. So if you're only putting in some information, not the full host list and stuff, the data that you get out may not be top notch. And this is what the landing page looks like for data entry. So put in the insect taxonomic information. It's all like drop down menus and stuff. But again, the biggest area for putting info in is the native host trees. That is the most significant factor. And then secondarily insect feeding guild and then taxonomy. So, but native host trees, giving that list is really important. So, and then you'll just hit run model and then it'll run a risk report for you to kind of figure out what something is. So, our product so far, again, iTree Pest Predictor is probably one of our bigger products. We have 5 papers that are now out, 3 databases that are now out. So if y'all want to take any of our data and run with them yourselves, you're welcome to. We have a lot of presentations and stuff, and there's more to come. We're still working on this. So just sort of summary of the tool, we feel like it has a lot of implications for pest prediction. It can predict the probability of impact. It does not predict the probability of establishment. That's gonna be a whole different set of criteria to determine whether an insect will establish or not. And something that we did not, I don't know, consider when doing this. That's a different working group altogether. Some upcoming products, so we're writing a paper on iTrue Pest Predictor now, just to kind of say, here's the tool, here's how to use it. We're also writing a manuscript about our databases, just to say, here's knowledge gaps. This is also a call for foundational research. I like giving the spiel every single time I give this presentation, because going through the literature and trying to find even basic information about insects is so hard. The information is not there. So, I don't know, whenever you're talking to funders and stuff and talking about like the applications of your research, even basic research, like figuring out the volatinism of an insect, or I don't know, feeding yields or whatever, identifying the insects themselves, that is so important for more applied stuff like this. So, in the next phase, we are continuing this work. We had a lot of people come to us and say, okay, cool, you have iTrue Pest Predictor, but I really don't want to sit down and synthesize hosts and enter all that in, like, that is beyond me. So we are now in our next phase of doing that work for people. We are putting together a risky insects database where we collect host data, taxonomic information for insects around the world. Europe has some of the best documentation for insects that we can find. And so we started with Europe. So we have so far collected information for 300 herbivorous insects native to Europe that have not yet established or been introduced into North America as far as we know. And so we put all the information into iTrue Pest Predictor. We are running analysis now to just sort of see which insects are going to have the highest impact, which trees are most at risk. North American trees are most at risk. And then what is the overall sort of impact? Are there any particular regions that are going to be like really, really massively impacted if any of these insects come in? So we're trying to break it down and like feed information to like policymakers and stuff, because they don't want to do all this. We're doing it for them. So I envision this probably being a lifelong, career-long pursuit, synthesizing all of these data and putting them in and coming up with these sort of like short lists of, do not let this in, this is the type of product it comes in, here's how we can kind of do phytosanitary regulations or whatever to prevent this from getting here. So, I don't know, I like to think that this is impactful research and that we can make a difference. But we still have a long way to go before it can be like truly applied at a policy making level. So that is all I got. I'm sorry if I went over, I can't remember, 12:15. Okay. Right at 15 minutes then. Okay. So yeah, my email's up there. If y'all have any questions after the fact, I'm gonna holler at me. Again, acknowledging all of my collaborators in the high impact insect invasions working group, as well as all of our funding agencies. We were initially funded through the USGS Cal Center, and then we got a National Urban and Community Forestry Advisory Council grant through the USDA Forest Service. So they're the ones who kind of helped us do what we've done so far. And like I said, we're working on other funding now to figure out our next steps. So thank you all for your time and attention. It's a lot, I know, to throw at y'all, and there's a lot of data there. There are a lot of data there that we're still looking for. Like I said, this is a call for foundational research. So if any of y'all do foundational research, even in the host sector, like I know I'm talking to forestry and environmental conservation. So knowing some of the traits of the hosts, like I said, we have 400 North American hosts in the database, but there are so many more that we could include that we just didn't have data for, that USDA plants didn't have basic like shade tolerance, drought tolerance, like that sort of thing, wood density. So there's a lot of value in having that information too, if y'all want to like build careers on that. I'm happy to stand by you and be like, yes, this research is important for things like this, because we need that data. And, I guess, did you have a question?
Oh, I always have questions.
I was like, I don't ramble on about I've done this talk a lot of times, and so I get some like frequently asked questions, so I can like answer those too preemptively. If y'all don't have questions, yeah.
Okay, so you found that 3.6 million years ago was the evolutionary distance for these species to attack certain species.
It's sort of the sweet spot, so,
Right,
or, yeah, between the native range host, so if the native range host and the North American range host diverged around that time, that North American host is gonna be more likely to be impacted.
Okay, have you like traced that back to any other things that may have happened around that era? Climate change, or just to see what?
Well, it's mostly, it's mostly from a context, it's not necessarily, it's just whenever they would have diverged and the distance, and I think it's mostly, again, I'm not a tree physiologist, but the impact that it has on evolutionary like defense mechanisms, like chemical composition of like foliar chemicals or terpenes, like those sorts of things. Because they are gonna be sometimes more suited to defending. So if they're very narrowly, those defensive compounds are gonna be very similar in composition, chemical composition, to where versus like far diverged is not an issue. They don't have anything similar in composition, but in that middle ground, they may be just off enough that there could be some problems with successfully defending against the insect. If that makes sense. So yeah, there may be other things too, like climate change or whatever that come into play with host evolutionary history, but we've approached it mostly from the host defensive compound perspective.
So you said nobody was doing this for pathogens at all?
Not that I'm aware of. I've talked to, well, no, I don't want to say that because I can't remember, Jeff from Forest Service, Jeff Williams, I think he was interested in doing it, but I don't know if he's made any progress on it.
Okay, in terms of like compiling the list of pathogens and.
Yeah, and he's done some semblance of it. I remember at Annapolis meeting, not this year, but year before, he presented on something akin to it, but he included like insects and diseases, and I was like, yeah. we can't do that. You gotta break it out more to have more refined predictions.
Yeah.
But I think that he was starting something then, but I don't know where he stands on it. Okay. But yeah, check with Jeff Williams. So you wanna tag team?
I'm not a pathologist.
Things.
But I know Jeff.
I know enough to be dangerous. I don't know enough about like I know some about like the evolutionary history. It's just so hard because pathogens are oftentimes, you can have alternating hosts. There's so much complexity to their life cycles. I mean, insects are complicated too, don't get me wrong. Pathogens take it to a whole.
They have different genera just depending
Yeah.
on whether they're sexually or asexually reproducing.
Yeah. So it's hard to predict with that. I'm sure it can be done, but also given that it was so hard for us to find enough information with the insects, I just don't know that there's enough knowledge about pathogens to do anything significant with at this point. There's gonna have to be a lot more foundational information provided to be able to answer those questions realistically.
So, your group just looked at North American introductions. So, has anybody or is there a group looking at like introductions into Europe or introductions into Asia and seeing if that's like a reciprocal relationship?
Yeah, that's a frequently asked question. So we do, so to kind of start answering that question, this does not predict those insects that may enter into Europe. This is just solely for insects that come into North America. But I have, through Nathan, been in communication with some European researchers who want to build their own models and predict whether a North American insect will be high impact in Europe, for example. I haven't heard from any like Chinese, Japanese, whatever, Asian researchers in that side of the Palearctic, but I have had communication with some European researchers who want to build it. I don't know if they want to do it for all of Europe or just like a particular country, but they want to build their own tools for prediction.
Yeah.
Too. So yeah, I think some people may be working on it, but again, I don't know the status of that. They aren't keeping me in the loop. I'm like, here's our papers, here are our data.
Have fun.
Here's our methods. If you need more info, let me know. But yeah, that's not my thing to pursue. So yeah, I'm happy to share info with anybody that wants to do stuff, do their own research based off of this. And there's so many, like I said, the data sets are online. So if y'all can think of ways that you can utilize the data to answer other questions, it's all there. You just got to download it. Okay, thank you.
So you know, it's like we only get. Yeah.
Yeah. Yeah.
I think that, yes, it's very recent.
Yeah.
I went to the one last year. I've been, I've been all day like semester. I'm barely here.
Thank you.
Also.
Sorry.
Travel up there every couple of weeks.